In this video, we solve this problem. It's an exact differential equation. It's from the written homework in the spring 2021 semester. Since it is labeled as an exact differential equation, we can just assume that that's true. But let's say it wasn't labeled as an exact differential equation. Since it's written in the form m dx plus n dy equals 0, we might think it's exact. We might also notice that if we replaced x with tx and y with ty, we couldn't factor out powers of t. So it's not a homogeneous equation. So if it's not, it's obviously not linear. You've got y squareds inside exponentials. It's obviously, or maybe not so obviously, not separable. But if you divide both sides by dx and then you subtract this expression from both sides and divide by that, you see that it's not separable. So it's not separable. It's not first order linear. It doesn't look like it's Bernoulli. It's not homogeneous polar. So the last method that we might try is the method for exact equations. Now, to solve an exact equation, we need to label this function, call this m of x, y, and we'll label this function n of x and y. And to show that it's exact, we will compute the partial derivative of the first function with respect to y, and then show that that partial derivative is the same as the partial derivative of this function with respect to x. So we'll start by doing that. You can use subscript notation or Leibniz notation for those derivatives. I'm going to use Leibniz notation over here and subscript notation over there. So we're taking the partial derivative with respect to y of 2y times sine of x times cosine of x minus y plus 2y squared times this exponential function. Now I can think of this as the derivative of a constant times y, because I'm treating my x as a constant here. The derivative of a constant times y is just the constant. In this case, the constant is 2 times sine of x times cosine of x, constant with respect to y. And the derivative of negative y with respect to y is -1. And then this requires a product rule, because that's a function of y times a function of y. So according to the product rule, the derivative of a product is the derivative of the first function times the second function undifferentiated, plus the derivative of the second function times the first undifferentiated. And the derivative of 2y squared with respect to y just requires the power rule. So you take your constant, multiply by the power, you get 4, and then multiply by y to the 1 less power. So that's just going to be a y to the first. The derivative of e to some power is e to that power times the derivative of the inside. And this time the derivative is a partial derivative with respect to y, treating x as a constant. The derivative of this constant times y squared is the constant, in this case x, times the derivative of y squared. So that's the 2 times y to the 1 less power. If we multiply all these together, we get this, 2 sine of x cosine of x minus 1 plus 4y times the exponential. And then you've got 2xy times 2y squared. That's going to be a 4x. Y times y squared is y cubed times the exponential. That's our partial of m with respect to y. Now let's compute partial of n with respect to x. Now, in order to do this, and just to make it a little bit easier, I'm going to write this sine of x, or this sine squared x, as sine of x quantity squared, just to emphasize that we're going to use the chain rule when we take this derivative. Because we've got this sine of x function inside a squaring function. So whenever we use the chain rule, we take the derivative of the outside function first. Derivative of a function squared is 2 times that function times the derivative of the inside. And in this case, we're using a partial derivative with respect to x. Derivative of sine of x is cosine of x. Now here I've got a function of x times a function of x, so it's appropriate to use the product rule. So we'll take the derivative of the first function and multiply by the second function. And then we'll add the derivative of the second function. Times the first function. And then we add the derivative of negative x with respect to x, which is just -1. And if y is being treated as a constant, the partial or the derivative of that constant with respect to x, that 2y is going to be a constant. Derivative of the constant with respect to x is 0. So we just need to evaluate this derivative and that derivative. Here we're thinking of y as a constant. So this is like taking the derivative of a constant times x. So the derivative of a constant times x is the constant. In this case, 4y is playing the role of a constant. And then over here, I've got the derivative of e to some power, and that power depends on this variable. So we get the derivative of e to that power is e to that power times the partial derivative of the inside with respect to x, treating y as a constant. Well, again, that's a constant times x. The derivative of a constant times x is just the constant. So we get 2 times sine of x times cosine of x plus 4y times this exponential. And then you've got 4xy times a y squared. That's going to be 4xy cubed times the exponential minus 1. And the claim is that these are equal to each other. These terms are the same, the minus 1s are the same, and these two terms are the same. So yes, since the partial of n, or partial of m with respect to y equals the partial of n with respect to x, since that's what we've just shown is that those, well, since those are true, then this is equivalent. That's equivalent to saying that these are true. That means that the differential equation is exact. And if the differential equation is exact, that means there exists some function f that depends on two variables, x and y, such that the exact differential of f, or the total differential of f, is equal to the left-hand side of that differential equation. That's m dx plus n dy. Well, by definition, that's the partial derivative of f with respect to x times dx plus the partial derivative of f with respect to y times dy. The only way that these two could possibly be equal, well, the only way that these two are equal, is if the partial of f with respect to x is equal to m and the partial of f with respect to y is equal to n. Now remember, when you're solving an exact differential equation, it comes from taking the level curve of some function, f of xy. So we'll have f of xy equals, let's say k, where k is a constant. And you take the exact differential of both sides. So just for example, I'm going to use an elliptic paraboloid as sort of a cartoon for our situation. It's not exactly what this function looks like, but just to help us remember what it is we're doing when we solve an exact equation. If we had this equal to a constant k, well, that would correspond to a particular level curve where z is equal to k. If we take the total differential or the exact differential of both sides, we get df equals the differential of k, which is 0. And the left-hand side is this, and the right-hand side is this. So the solution to this equation is actually going backwards through these steps. It's a level curve of some function of two variables. So we need to find f of xy, and we know its partial derivative with respect to x is m, and its partial derivative with respect to y is n. So we can find f by taking appropriate antiderivatives. So if I have the partial of f with respect to x, if I anti-differentiate that with respect to x, well, that will recover f partially. Well, if I have the partial of f with respect to y, same thing. If I want to get rid of that differentiation, I anti-differentiate with respect to y, and that will recover f partially. Now, with both of these pieces, we can figure out what f has to be. So that's what we'll do. The partial of f with respect to x is m, which happens to be 2x or 2y times sine of x times cosine of x minus y plus this function. y is being treated as a constant, and we're anti-differentiating with respect to x. So we'll bring the 2y down, and we can do a u substitution here. If u is sine of x, du would be cosine of x dx. So this times this would be our du. So this is the integral of y times 2u du. So we end up with, well, the antiderivative of u, if you prefer, if you've already taken the 2 down. The antiderivative of u with respect to u comes from adding 1 to the exponent and then dividing by the new exponent. And then, of course, you've got to back substitute. U was actually equal to sine of x. So this is sine of x, quantity squared, times y. Or if you prefer, you can call that sine or y times sine squared x. Either way, it's the same thing. Now, negative y is constant with respect to x. The antiderivative of constant with respect to x is that constant times x. And mathematicians like to make our variables alphabetical generally, unless you're dealing with trig functions when we break our own rules. And then over here, the 2y squared is being treated as a constant. And I've got e to a constant times x here. And I'm taking the antiderivative. If I was taking the antiderivative of e to the 3x, I would get e to the 3x divided by 3. Differentiating would require me to multiply by 3 due to the chain rule. Since I'm taking an antiderivative, I would divide by 3. In this case, I've got a y squared playing the role of that 3. So this is x times y squared. The antiderivative of e to the x times y squared is that, and then you divide by that constant, which is the y squared in this case. The y squareds reduce, and you end up with 2 times e to the xy squared. And you're anti-differentiating with respect to x. So our constant of integration is only constant with respect to x. It may depend on y, so we'll call that g of y. So f is this function, and it involves some unknown function g of y. In order to find g of y, we'll take the antiderivative of the partial derivative of f with respect to y, which was this much more involved function, sine squared x plus 4xy times this exponential minus 2x plus 2y. Well, that's just constant with respect to y. The antiderivative of a constant with respect to y is that constant times y. And then here, I've got a constant times y squared inside the exponential and a constant times y outside the exponential. So that's actually a really good candidate for a u substitution. So I'm going to write that just like that for right now. The antiderivative of negative x, which is a constant with respect to y, is that constant times y. And the antiderivative of 2y with respect to y is just y squared. And then we're going to add a constant of integration, but I think I'll do that when I evaluate this integral. So we've got y squared sine squared, or y times sine squared x minus xy plus y squared plus the integral of 4xy times this exponential. Okay, now over here, if we let u be the exponent, then du, if we're taking derivative with respect to y, is 2 times xy times dy. Now that's going to work because I can write this expression as a constant times 2xy dy. I want to make this a 4, so I'll multiply both sides by 2. And we'll have 2 du equals 4xy dy. So this is 2 du, and this is multiplying e to the u right there. So we get this. We have f of xy is equal to all of this. I'm just rewriting. Plus 2 times the integral of e to the u du. Oops, I keep wanting to square that y, but it's not squared. And that's just going to give us a 2e to the u plus something that is constant with respect to u. But remember, u is actually this x times y squared, and we're substituting for a partial antiderivative with respect to y. So the constant of integration should not depend, it should be constant with respect to y, but not necessarily with respect to x. And then of course you have to remember to back substitute. U was x times y squared. Okay, so f is equal to this. And if we've done everything correctly, f is also equal to this. Question is, which or what are these functions, h of x and g of x, or g of y? Well, I've got this and this, those match. That's what f is. I'm trying to figure out what f of x, y is. So it has a y times sine squared x in it. It also has a negative xy in it. It also has this 2 times the exponential e to the xy squared in it. And then the parts that don't match are the g of y and the y squared times or plus h of x. Well, if g of y is y squared plus a constant and h of x is the constant, that will work. So you should always check and make sure that this satisfies both. We've got this plus this plus this, yes, plus a function of y alone. Y squared plus c is a function of y, great. This should also match this. It should be this plus this plus this plus the y squared plus a function of x. The function of x just happens to be c. Okay, so that's our f of x, y. And again, remember, the solution of an exact equation is a level curve of some function of 2 variables. So f isn't the solution, it's f equals a constant that's equal to our solution, or that is our solution. So we have y times sine squared x minus xy plus 2 times this exponential plus y squared equals that constant. And I'll just use a constant k, and I'll let k absorb that c. So that is the solution of our exact differential equation.